Okay. Right, so thank you very much for the invitation. It's very nice to be asked to speak on this subject. So we've been thinking about it, well, myself and Keith Dina since about 2015. We started in the GGI actually in Italy, and this was really resurrecting some kind of ideas that he'd had from the 90s. So this was the early 90s. He was thinking about things in non-supersymmetric string theory. So I want to tell you sort of the work that's come out of that and things that we're doing right now. The remit I was given is to give you a kind of phenomenologically useful overview of this subject. So I'm not really going to talk too much about model building and that type of thing. I'm going to just really talk about the properties of string theory that make things happen. So that, for example, that make the theory remain finite. So, so this is an overview. So first of all, I'm going to, why do we study this at all? So what's so interesting about non-supersymmetric strings, apart from the fact the world is non-supersymmetric? And then I'm going to tell you about sort of 4 lessons, basically, that you can learn by studying them, which tell you how a UV completion will make a theory finite and what happens to it when you do things to the theory. So what you want to understand, for example, when a theory will be natural. And so at the end, I want to get to this point, so right at the end, a general naturalness condition for string theory, which actually at the moment there isn't really. So we're going to present an equivalent to a field theory naturalness condition, which is essentially telling you when a string theory, what you need to do to make a string theory natural. So, so why study this subject at all? I mean, so the world is non-supersymmetric, as we know, and it is getting less and less easy to satisfy supersymmetry and confront experiment with it. So that's the obvious thing. But then the other thing is that if you're thinking of a UV completion, supersymmetry kind of obscures the properties of the UV theory. So the UV theory, to make itself finite, is doing all sorts of amazing things that are not apparent if you make it supersymmetric. So the theory underlining string finiteness, and I'm going to be talking in this talk about heterotic strings. And so the symmetry which is underlying their finiteness is modular symmetry. And that's really a kind of number theory property. It's nothing to do with supersymmetry at all. And the modular symmetry really does already miraculous things for you that the supersymmetry kind of obscures. So it kind of becomes more beautiful, actually, if you make it non-supersymmetric. And then there's a couple of general observations. So the first is that UV finiteness, if I insist on it, is very constraining. So you can ask, if I look at a UV sensitive operator like the Higgs mass, what does the UV finiteness tell me about it? So that's really a naturalness condition that I want to look for. And then the second observation is that supersymmetry is broken, but finiteness is not of the string theory. So that if we say that the theory is finite and modular invariance is Y, the theory has to be finite and modular invariant today. So anything we can say about it because of modular invariance is true today. So that's why it's an interesting thing to think about. So in this talk, I'm going to sort of take those general ideas and give you 4 sort of lessons, phenomenology lessons, things you can learn by studying non-supersymmetric strings. So just before I continue, I should just sort of should alert you to the fact this is not a subject which is entirely run by us. I mean, it's an old one that started right at the beginning of string theory, essentially. So the early papers are in the 80s, and then there's a connection with thermodynamics, a thermal string theory. So Atkin, Witten, and friends. There was a great interest in that, and then Keith and various people came along after that. So we're not claiming to own this subject, but we are following our own furrow in it. So that's what I want. I'm going to give you our outlook on it. So the first thing we can discuss is when you if we're living in an effective theory, what is it that we can say about UV sensitive operators? And essentially the answer is nothing. So if all I know is that the world is non-supersymmetric, there's nothing in particular that the effective theory is going to tell me about it. And so we can see this. So it's called the Proto Graviton theorem in the closed string theory, and this is already this is a paper of Keith's in 1990. Okay, so this is not a new fact, but it's been there and it's kind of rediscovered every so often. And it's really, the principle is a UV sensitive operator, such as a mass, will not be restricted by what's in the effective theory. So I'm going to start with something fairly simple and just show you why that's true. So how can I make such a general statement like that? So suppose we're going to calculate a cosmological constant, lambda, in some number of dimensions, d. So this is what it would look like in the string theory. And just in case you're not familiar with the way it looks, this is, you're summing, you have to integrate over all possible partition functions to get your cosmological constant. And so it looks similar to a one-loop diagram in a Schwinger parameterization, except the parameter is now two-dimensional because it's a world sheet. And the object that appears in the partition function is written normally in terms of this parameter q. So q is e to the 2 pi I tau. So this thing is normally called a q expansion. Anyway, so thanks to modular invariance, you're supposed to integrate over all independent taus, which describe the different tori. Modular invariance tells you that actually I can map up every different torus into a fundamental domain. So famously, you're missing the part down here, which is the ultraviolet of this integral, and you only get this part, which looks like the abnormal field theory. So if I boil this integral down, what you end up with is something that looks like that. And so as an approximation, the 1 here is the bottom of the fundamental domain, the 1, and then this is some cutoff, so I'll put an infrared cutoff here. And you see this thing, it looks just like a Schwinger integral. So if I was calculating a one-loop potential, Coleman-Weinberg, that's what it would look like. And these parameters, the a and n's, they're really just counting the number of states weighted by statistics, so bosons minus fermions. And then there's this exponential e to the minus Schwinger parameter t m squared. So you see that this combination alpha primed pi tau 2 is your Schwinger parameter. Okay, so that's what it looks like. And it looks like, okay, so this looks just like the field theory, so we must have a good idea of what should happen to lambda, but actually you don't, because you know that in the theory you have this state on the right here. So the state on the left is the graviton, and if the graviton is there, which it ought to be, then so is this state on the right. And no orbifold projection, for example, can get rid of the thing on the right if the thing on the left is there. And the thing on the right is not a physical state, so it's not level matched. So the right moving side is massless and the left moving side is tachyonic. However, the fact that it's there means that whatever my partition function does, the z, this function I put into the integral, it begins like this, d minus 2 over q plus dot dot dot. And so it's this, if I put this into the integral, I can do the integral and I evaluate it, I find I get a large contribution because this thing can contribute because of the curvedness of the fundamental domain at the bottom. So if I was just integrating across here, the physical part here, I do my tau 1 integral. If I just go back here, I do a tau 1 integral, I get 0 unless m is equal to n. So that forces level matching the integral across the taus, tau 1. But down here it doesn't, and so I get something, and that something can actually be dominant. And for a generic radius, if you like, a generic compactification radius, generic theory, it will be the dominant contribution to lambda, whatever else is there in the partition function. So your QFT intuition is not going to help you, and there's no guarantee any UV sensitive operator, there's no guarantee the QFT is going to give you anything like the real answer. Okay, so that's the Proto-Graviton theorem. And so kind of inspired by that, we in 2015 decided to to try and look for something which would make it possible to construct, nevertheless, a non-supersymmetric phenomenology and have control over it. And essentially, the problem boils down to the fact that your lambda, so this object here, the fact that it's non-zero means that there's an instability in the theory, because I can attach a dilaton to it, and the dilaton's uncharged. So this tadpole in principle is there, and it's going to mean that the theory is unstable. It will run away, and the instability will be a kind of string-sized one. So I'm not going to be able to do anything with the theory. And so our approach was, instead of trying, so you see that this comment here, that no one has constructed a non-supersymmetric four-dimensional heterotic string with vanishing cosmological constant. If that were possible, that would be very nice if it was in a stable minimum, but it doesn't seem to be possible. It's not very easy to achieve, or it's impossible to achieve, apparently. And so the idea was that we should forget about trying to look for something which is absolutely stable with lambda equals 0, and all we require is that lambda is sufficiently small. So we just need to split lambda from the string scale. And that's what we want. So this is our objective. We want to get C much less than 1 in string units. That's the essential, I mean, it's the first step, if you like, to constructing a phenomenology. So, okay, so this is the problem. That's Proto-Graviton theorem. So, and so the way to do it is via interpolating models. Well, this is the construction we came up with. And so here's the lesson underneath. See the lesson that you learn in brackets, which you'll learn right now. When I change something in the whole theory, the entire spectrum has to change out from top to bottom, so up to infinity. So that is something that you're about to see when I describe this. So, you know, even just electroweak symmetry breaking, if we do that now and you assume that there is a closed string theory completion, electroweak symmetry breaking will shift everything everywhere, has to, for modular invariance. Right, okay, so an interpolating model. So what's an interpolating model? The first example of it was this phenomenon was Itayama and Taylor's configuration, where they showed that if you want to consider the non-supersymmetric SO16 cross SO16 theory, which has a non-zero lambda if you calculate it, what you can do is I can compactify it down to 9 dimensions with a Schwartz compactification. Actually, I can begin with the E8 cross E8, do a compactification to 9 with a supersymmetry breaking compactification. So that is one that is proportional to 1 over the radius. So the gravitino mass is proportional to 1 over the radius. If I make the radius become very small, what happens is it will tend towards this other theory, the SO16 model. So these are 2 10-dimensional theories, but they're joined together by compactifying to 9 dimensions and then going from large radius to small radius. So this is the paradigm of this interpolation theory, is that you have a high dimensional theory here, which is supersymmetric. You have a high dimensional theory here, which is also which is non-supersymmetric, both 10-dimensional. In between, you have a lower dimensional theory, so 9 dimensions in this case, which has broken supersymmetry. And actually, so what happens is if you take this general configuration and I just look around here, what you find is that you have a theory which looks like softly broken supersymmetry. Looks like softly broken supersymmetry. See, I italicized the looks because well, I mean, the thing which I have to struggle to define is what I mean by softly broken, because if I look at the ultraviolet of this theory, it's actually completely non-supersymmetric, but I can write an effective theory which looks a bit like it, that's a softly broken SUSY theory. Right, okay, so this is the general configuration which you can do to do some phenomenology. And so this is what we came up with, is you begin with, well, so here, big D was 6 for us. You have a supersymmetric theory at large radius and a different theory at small radius, which is non-supersymmetric. And in between, you've got a D equals 4 theory, so I compactify 2 dimensions. And I vary the radius, and I get something where I can control the cosmological constant and I can make the Proto-Graviton contribution be much smaller. So R, the radius, is a control parameter, which allows me to restore order, if you like. I can dial down my Proto-Graviton contribution so that I can still think of it as a field, in a field theory sort of way. Right, so this is what's happening to the partition function as I do that. So you can think of it as having two components. One belongs to the non-supersymmetric theory and one belongs to the supersymmetric one. And as I change the radius, the contribution from one half will die away exponentially and leave the other one. So as my radius goes to infinity, I'm left with something which is this thing, which is supersymmetric with a volume factor. So I get the R to the D volume factor for the partition function. And if R goes to 0, I get something which is non-supersymmetric. Right? So that's the way that the phenomenology jumps out of it, falls out of it. So, okay, so that's our setup, and we do phenomenology with that. So I'll show you what happens. But before I do that, I'm just going to show you what's happening to the spectrum when I do that. So this is kind of the miracle of what the string theory is doing for you. So what I'm showing you is it's the Bose-Fermi non-degeneracy, so NB minus NF. So that, remember, so I don't know if you can see that, I called it A. So A underscore NN. So these are physical level match states. And this number is the difference of bosons minus fermions. Right? So if it's supersymmetric, this would be 0. So clearly supersymmetry is broken. And A, little a here, this thing, this is 1 over the radius. So this is a radius of order 1, this spectrum here. And you'll see that, and this is the logarithm of the number. So these numbers are becoming huge. You know, this is e to the 30. Number of bosons minus number of fermions is e to the 30. And so it's a terrible non-degeneracy. It's completely not supersymmetric when the radius is order 1. And yet the answer is finite. That integral is finite. And so this is what happens as I increase the radius. So little a, which is the scale of supersymmetry breaking, if you like, 1 over the radius. What happens is, as I increase the radius, the spectrum changes. So you see that what happens, it begins to become supersymmetric down here. So at the bottom of this ladder here, it's looking, you get the steps. And so you see that this jagged step here, which is constant, this is a broken supersymmetric spectrum, this one. And these are Kaluza-Klein modes, so they're separated by, so this separation is the Kaluza-Klein separation. And the steps are due to string excitations, right? So the string excitations are much larger than the Kaluza-Klein difference at this point. But you see what happens is, as I get heavier and heavier, so I get to this point, all of these objects here, they're completely non-supersymmetric still. And that this you can think of as the winding mode part of the theory, and it belongs to the part of the theory at r equals 0. So it's never going to go away. It doesn't matter how large the radius is. This part, the completion, the UV completion, will always be there somewhere. So if the radius is, the larger the radius gets, the more it goes over to the right here. But it will be there at some point. So you can't get rid of that ever. So this is the strange thing that happens when I break supersymmetry with Shirk-Schwarz, and probably at all, is that the spectrum will not be supersymmetric all the way up. It's only really in the effective theory that it looks supersymmetric. But really there's no supersymmetry in the UV. So you see, this is what supersymmetry is obscuring, is this behavior, which is actually the interesting part. Anyway, so if we want to do phenomenology now, we can deduce very generic behavior. And what you can think of as going on here is that when the radius is large, so when I'm in that part of the theory where I can control it, I am essentially looking at the Casimir energy of the compact dimensions. And so that lambda, my cosmodular constant, is going to go, when I compactify to 4 dimensions, like 1 over r to the 4. And so, this is the generic situation. My radius dependence in the cosmodular constant goes like 1 over r to the 4. But there is a kind of interesting sort of theory, which is when the number of bosons is equal to the number of fermions at the lowest level. So this is at the 0 excitation level. And if that's the case, then the Casimir energy vanishes at leading order. And so at sort of the first contribution at one loop is going to look like it's going to come from the first excitation, but it's going to have this exponential suppression there because it has the excited mass. So M1 is the string mass. And so Rm1 is large. So for moderate radius, the one loop cosmological constant can be exponentially suppressed this way. And so this is our recipe for things which can be metastable. So this is the kind of starting point for doing phenomenology. Okay, so those are interpolating models. And let me just show you what these theories predict for you. So this is the useful lesson we learn. This part is that if you look at what is happening in the UV theory, so here we have an NB equals NF requirement, you do get predictions for the phenomenology. So this is what I'm going to show you. So the technique, there are, by the way, techniques for constructing these things. So that was part of a large bulk of this paper. Of our first paper was really to how to construct theories which have got NB equals NF. And you can find things which look like nice, so standard model like chiral, 3 generations and so on, and also gut-like, and work was done on cosmology with these things and so on. So they have a very rich phenomenology that's possible, but the thing that you're interested in, phenomenologists, is what can I say generally about the phenomenology that I would expect without having to build anything. So this is the first thing you can say. If I insist that NB equals NF, then I know that, so that's true for all of the Kaluza-Klein modes, but it is reflecting what is happening in the massless sector. So if I look at my observable sector, I have to match it NB minus NF, which is not 0 nowadays. I have to match it with a hidden sector. So the first thing that you can conclude is that a hidden sector is kind of inevitable in these theories. You can't really avoid it. And if you look at why the cosmological constant is suppressed, it's that a cancellation between modes in the Kaluza-Klein towers of the hidden sector and the visible sector. So this has a net fermion number, and this has a cancelling net boson number. And so it's that's the cancellation that's making this sort of compact Casimir energy, that's compactified Casimir energy contribution small. So that's the first conclusion. There were 2 other ones. So the first one is that generally, when you try and construct something, it's impossible to just keep the Schwartz breaking on the space-time degrees of freedom. It has to get embedded in the grand unified theory. And so that gives you 2, it has to break a grand unified group. So that gives you 2 predictions. One is that you get this, what we call gut precursors. So that's essentially that your Kaluza-Klein levels are already going to show some gut states in them. So they're going to kind of fill up gut multiplets. And then the other interesting thing is what we called entwined SUSY. And that's if you look at the low energy theory, so that's the theory today, and you look at how the couplings are, you'll find that it looks as if they're dropping out of a superpotential. So you can imagine that. I have states sort of in a MSSM assignment, so Q, D, and H, and E, L, and H, and so on. And but what happens is there's another charge, which is the charge associated with Schwartz breaking. So that's this in 0, half 0. And this charge tells you if the state is going to be light or not, and whether the fermions are going to be light or the bosons of that supermultiplet. And so what happens is that in some of these supermultiplets, the fermions remain light, and in some, the bosons remain light. And so what you get in the massless spectrum is a kind of something looks a bit like folded SUSY, if you like, in that some part of a supermultiplet is there, but it's filled up, it's completed by another part of a different supermultiplet. So you get this, so what we call entwined SUSY. You fill up supermultiplets, but the charges are not degenerate in a supermultiplet, if that makes sense. Right, okay, so that's, okay, I'm kind of running out of time, but just to finish, I'm going to tell you what we're talking about right now, which is, so how to get a string naturalness condition. So if I want to start thinking about when a theory is natural or not, and I'm thinking of something which I'm assuming is going to approximate a string theory or look like a string theory, I want to know what string naturalness looks like. And so in order to see that, we need to go back to the spectrum and look at what the spectrum is telling us about the order of the theory and how it makes itself finite. So I'm going to talk about that, and the string naturalness condition will drop out of it at the end. Right, so I'm going to go back to this diagram, which is the spectrum. And so remember, this is the kind of Bose-Fermi non-degeneracy of the theory. So boson number minus fermion number, logarithmic. And this is the thing which, in a sort of crazy sum, if I sum over this thing, if I do the integral for the cosmological constant, it's a finite lambda, despite the fact that the states are doing this. So counting states would indicate the thing ought to be ridiculously large and infinite, but it's not, it's finite. And the reason for that was noticed by Keith Dunes in 1994. So this is the misaligned supersymmetry. And it's one way to understand what's going on. And the way to see it is that to take your lambda and write it in a different way. And the thing that allows you to do that is modular invariance. So this integral over the one loop tau parameter, which I use to get my lambda, there are various theorems and so on which tell me I can write it as a supertrace over the physical states. So I just look at the level match states in the theory. So those are the ones with n equals m, left moving, right moving masses are the same. And I can write my lambda like this. So it's a supertrace over all of those mass squares, the physical mass squares, up to infinity. And this is the string mass, the curly m here, calligraphic m, with a 1/24. So you see it's very precise, this thing. And you may also see that it actually looks like the first term in the Kalman-Weinberg potential. Except we know instead of a cutoff, we actually have a number. We have the string scale in there. But otherwise, it looks a bit like it, but it's actually completely the opposite thing. It's a supertrace over the mass squareds of all of the states up to infinity. There's no cutoffs at all. So it's not a field theory object, although it looks a bit like one. It's really a sum over the infinite Tarot states. Right, so I'm going to show you how this result comes about. So how accurate are you with the timing on these talks, by the way? Am I allowed to steal a few minutes? Okay, I'm going to continue.
You have about 5 minutes.
5 minutes, okay. That should be okay. Right, so this is how to understand why that strange expression is valid. So this is the integral we're actually doing. So z is the partition function, and remember that's this Q expansion form. And so we want to do that integral, and we want to write it in terms of all the physical states. So those are the level matched ones. And if I want to extract those, I can define this thing. So I'm going to call this the net density of physical states, d_phys. And in order to get it out of z, all I need to do is to set the levels the same, right moving, left moving. So I can do an integral over tau 1. So that's kind of integrating over the fundamental domain that way. So I do that integral, and it extracts for me this object here. So that's just, it's kind of like what you would put into what appears in the Schwinger integral at the end. It's the same object. So I'm going to look at that thing, and I want to extract from that the for lambda. It's one way to do it. I mean, there's various ways to do it. But the best method I think of, I mean, the most beautiful method is by Rankin and Selberg from 1940, actually, and then Zagier has an extension to it. And so this is their formula. So they say that lambda is 2 times the residue at little s equals 1 of this transform. So I take my physical density of states, and I do this integral. I do that integral. Looks a bit like the Schwinger integral I would do, except I put in this little s there. And I end up with this thing, which looks a bit of a mess, but I take the residue of that s equals 1, and it gives me that answer. So this one gives me that. So it's just it's an exercise you can do. If you're sitting there with your Mathematica notebook open, put this function in, take the residue at s equals 1, you'll get 1 over 24 times by the m squared, which is what you want. And what this thing does, I mean, it's an amazing thing, the Rankin-Selberg technique. And what it does is it takes this integral and it unfolds it onto this strip, onto the strip here, which is called the critical strip sometimes. And it turns it into an integral. You see this transform, it's an integral over all tau. So it's integrating from 0 up to infinity. And that's what it does. It turns an integral over the fundamental domain into an integral over the whole tau2 going from 0 to infinity. And so you see that now what it's doing is it's including all states of masses up to infinity, which are kind of there. So that's how lambda is turned into something which is a supertrace. Right, so now let's look at some other operators, and the other operator we're interested in is the mass squared of the Higgs. And I'm going to just infer what it should give me without doing any model building at all. I'm going to infer that if I have a scalar which is a Higgs and I want to get its mass squared, I ought to be able to take lambda and just take a double derivative. So in the field, so I'm thinking it was a background field. I take a double derivative of this phi. And what I do is I will pull down some charges. So this is like a Casimir squared charge. But that thing, if I just pull down q squared, it's not a modular invariant object. The integral won't be modular invariant. I have to complete it. And so what happens is, if I pull down, say, this is for the left moving q squared, I have to modular complete it with a right moving q squared and some 1 over 4 pi tau 2s. This object with that insertion, so I'm being a little bit schematic, but you take the z, you put in this operator, you put in that particular combination of q's, that thing is a modular invariant combination. So I can use the Rankin-Selberg transform for that. And that's what the Higgs mass squared should come in. Right, so now we do the same operation. So I do get my Rankin-Selberg transform, which is that. I then come across a little bit of a problem because it's logarithmically divergent. So you see that this g here, this g, will have a term in it which goes like linear in tau 2. And so when s goes to 1, so I want to do my Rankin-Selberg transform, I take s to 1. This turns into something which is a logarithmic divergence. And so I have to cancel off that thing. And that corresponds to the exactly massless part of the theory. So the bit in g, which goes like tau 2, has to be cancelled with some coefficient in order to make sense of it. So that thing is an identity still. So this is Zagier's extension of the Rankin-Selberg transform. I can still do that, and that is perfectly finite. But now I can start to think like a field theorist and say, well, I want to now cut off my tau 2, and I'm going to call that my energy scale. And I'm going to treat all the states whose masses are below some scale mu as if they were massless, and I'm going to subtract them. And then I get something that looks like a renormalization scheme and a renormalization procedure, where the numbers of degrees of freedom are going to depend on mu. Right, so that's the Rankin-Selberg technique, and then this is the answer you get. So at the end of the day, when I take that operator, I expand it, I do the Rankin-Selberg technique, you see that you get these 3 components. So the first piece is it comes from the product of the bits that don't have q squared in, and it's just a cosmological constant. This is independent of how the cosmological constant is there. It could have a large proto-graviton contribution. We don't care. This term is just the cosmological constant, guaranteed to be, plus something which looks like a double derivative of everything whose mass is larger than mu. So that's the energy scale. So this is like the double derivative of the cosmological constant, plus something which looks like the first logarithmic term in the Coleman-Weinberg potential from the part of the theory we had to subtract. So that's everything with mass less than mu. So you see, we're kind of deriving various interesting things at this point. We've got we have sort of combining hierarchy problems. So we're calculating a mass squared, and we're relating it to a cosmological constant. And then, in addition, we're deriving a Kalman-Weinberg sort of potential. So we get a naturalness condition, which is that thing, this object, the supertrace m squared, the double derivative should be smaller than the mass squared of the Higgs that we want. So this, I'm going to call it the anti-Veltman condition. So you're probably used to a Veltman condition. This is kind of the opposite. So this supertrace is over everything that's not in the effective theory, which I am much more comfortable with as a naturalness condition than looking at the effective theory. Okay, right, so I should stop there. Sorry, I've gone over time. Right, so to conclude, it's really vital to consider the complete non-supersymmetric theory to say something meaningful about and new about UV-sensitive operators. So in this particular example of theories, heterotic ones, modular invariance is really telling you an awful lot about what the phenomenology can be. So if you don't insist on integrating everything out, you can learn some interesting things from the UV completion, and you get precise supertrace relations for UV-sensitive operators, which are really kind of mathematical identities, which allows you at the end to get a naturalness condition. Okay, thank you. I'll leave it there.
Okay, thank you, Steve. So we have time for some questions. There were already some questions in the chat that were answered by Dean, so let's give priority to more questions.
Yes, hello, I have one question.
Right.
In your presentation, you relate the Higgs mass to the second derivative of the cosmological constant, the vacuum energy. That would be okay if that cosmological constant were caused by the symmetry breaking that produced the Higgs in the first place. But your cosmological constant, at least, it didn't appear to me to be related to spontaneous symmetry breaking and the Higgs mechanism.
Oh, I mean, no, I don't think that's true. I mean, the cosmological constant, it will get a term that's constant, possibly, plus something which is dependent on the breaking. The constant won't appear in the mass, it will just be flat. So if I'm just interested in the mass squared of phi, I can really just take the double derivative of that object. Does that answer your question?
Well, no, I think you have to take the double derivative of that, of the energy that was generated by the symmetry breaking. Oh,
I mean, yeah, but we are doing.
Well, that's the only thing. Well, okay. I mean, I'm just saying I missed that. I'm not saying.
Oh, okay. Sorry. Yeah, but so essentially, we are doing. We're looking at the cosmological constant with the phi inside it, and so the whole thing still has to remain modular invariant when I adjust phi. So there's a lot of you have to be careful that you don't break modular invariance with phi. The whole thing remains modular invariant when phi has a vev, and then you take the double derivative of the whole object.
Oh, okay.
Yeah.
Okay. More questions? Actually, I do have maybe a naive question as a phenomenologist. I was wondering, in this kind of construction, do you have the possibility of a landscape like in supersymmetric string theory? Because that, in principle, could help with the cosmological constant problem. I mean, if you buy anthropic arguments, is it the same? Is it different? Because I know that supersymmetry can stabilize some of these fluxes. What's the story?
So that's a very interesting question, actually. Yeah. So in principle, there is a possibility of a landscape. It would be very interesting to be able to do it in this kind of modular invariant way, to put in a landscape into it. I mean, I don't see why you can't. You could have several scalar fields, for example, that sort of thing. Actually, Keith, I see sitting there, has done something similar to this, but I'm not sure it's not quite that. But
sorry, I wasn't able to hear you. What was?
Okay. Okay, never mind. But yeah, I mean, I think it's an interesting point. It would be nice to be able to do. Be very nice to be able to do a landscape, and I don't know if anyone's really looked at it.
Oh, landscapes.
Yeah.
Yeah, there has been work looking at the landscape of non-supersymmetric heterotic string theories. I think I probably was the first paper 2006. But there have been more recent studies, including all the way up to just a few days ago on the archive. There was one from Faraji and his collaborators. It's an interesting question because one needs different techniques to survey the class of these strings. There can be free fermionic constructions. There can be other ones that are overlapping, such as orbifold constructions or Gepner models. There are many different classes of these things, but people have studied the distribution of cosmological constants at one loop in these theories and other properties. And yeah, it's a very rich space.
Okay, thank you. I think we have time for one last question, if there is.
Oh, so by the way, does anyone recognize this apple tree? Do you know what this tree is? This is the apple tree that Newton had his apple fall on his head from. Apparently, it's still there in Lincolnshire.
Maybe I can ask one last question.
Yeah, please.
Early in the talk, you talked about softly broken, which makes it sound like you're going to get a Lagrangian, which I didn't see. And it's like you have some supersymmetry, but it's broken. So what does non-supersymmetric really mean? Does it include those things?
Oh, right. Yeah. So it does include those things. But when so the thing that we really wanted to avoid is to rely on supersymmetry to start with. So these expressions are completely not assuming any supersymmetry. So they would be true for any theory, even kind of SO16 cross SO16 or something. And breaking a symmetry in those things, it should still apply. And so in order to get a naturalness condition, you can't presuppose supersymmetry because then I'm already assuming what I want to solve. So, but it does include supersymmetric theories, these expressions.
Yeah, the point is, Gordy, as I was explaining in the chat, these theories only resemble softly broken SUSY in the limit that the radius has an extreme value, which was the point of the limited class of models. But even in that case, it only tends to make it look like broken SUSY at the very lowest levels. And as Steve explained really nicely, at higher, there's always, before you hit the UV limit, there is always a breakdown of it. It is never supersymmetric or even broken SUSY or anything that resembles broken SUSY. So it's a whole different mechanism. So there's a UV cloud of physics around it, which has nothing to do with supersymmetry, which is nevertheless controlling the divergences and keeping.
Okay.
That's what string theory is doing.
Yeah, it's a kind of the term softly broken is something which bothers me a little bit because it gives you the impression that if I go above a certain energy scale, it will start to look supersymmetric. It's actually the exact opposite, that it starts to look completely non-supersymmetric.
Okay, but you use it. But if you could choose to run down an energy step by step and go past the Higgs transition where you dump 10 to the 50 GeV into the vacuum, and then your formalism gets rid of that somehow. So what happens to get rid of that?
Oh, I mean, so we don't have, I mean, with these last expressions here, we don't have a solution for the mass squared. Or are you talking about the cosmological constant one, the NB equals NF theories?
You get it.
I think what he's asking is, are these relations disturbed? See, we're not solving the hierarchy problem. We're unifying the two. We're expressing in the top line in the box, the Higgs mass is related to the cosmological constant. So both of the hierarchy problems are together now an issue, but they're unified. A gauge theory thing and a gravity thing are unified. That is what you expect in string theory, which unifies these two ideas. But the point is that as you're running down in your way of thinking about it, which is not really how you should think about it, because this is not an effective theory kind of thing, string theory, but as you do, as you pass through phase transitions, everything is going to get upset. The winding modes will get light, KK modes will get heavy, string modes will move around. There will be a major disruption, but it is so that everything still has to wind up in a whole different position where still the supertraces vanish, where everything we've done is correct, because modular invariance is still guiding this. Misaligned SUSY is guiding this. So the relation that Steve wrote will survive no matter what, even if there is a disruption in how the states conspired to produce it.
Yeah, I mean, so technically, so you see that there's the m greater than mu and m less than mu. If mu is something like, say, a gut phase transition or something, you go below that, and you would normally, in field theory, want to integrate stuff out. And so what would happen here is technically, you would have to somehow, in a modular invariant way, get all these states to be heavier than mu, and then you would put them into this term here, into the first term. They would fall out of the logarithmic term, and they would go into the quadratic one.
Okay, so I think we can thank Steve again, and we can move on to the next talk. So please, Steve, unshare your screen.